So our speaker tonight, we're very welcome, very appreciative for Professor Hayley Fowler to join us from the University of Newcastle. Hayley Fowler is a professor of climate change impacts in the School of Engineering at Newcastle University, and her research focuses on improved physical understanding of changing precipitation extremes and providing better projections for climate adaptation. She's pioneered new downscaling techniques to bridge the gap between climate modelers and users of climate scenarios. Her many credentials include being a Fellow of the American Geophysical Union, a Royal Society Wolfson Research Fellow, a contributing author for the IPCC Assessment Report, and the UK Third Climate Change Risk Assessment, and is the past president of the British Hydrological Society. So we're very grateful and honoured to have you with us tonight, Hayley. And her talk is titled Future Changes in the Frequency of Extreme Weather Across Europe, with the summary being that European scale convection permitting climate models and ensemble predictions over the UK have been exploited to examine changes to extreme weather and their compounding impacts with global warming. This talk will present the findings in terms of changes to these types of extreme weather and possible compounding extreme weather events. The analysis suggests that not only warming, but dynamical circulation changes are important in the manifestation of change to some types of extreme weather. These projections have been used to provide the first analysis of impacts on infrastructure systems using a new consequence forecasting framework and show the implications for adaptation. So that sounds really interesting and look forward to hearing it all. So without further ado, over to yourself, Hayley, and we'll catch up with the Q&A afterwards. Over to yourself.
Thanks very much, Gregory. Let me work out how to share my screen, hopefully. Yep. Okay. Right. Is that working for everybody? I'm assuming it's
working fine. Yes, it
perfect.
is.
Excellent. All right. Well, thanks very much for welcoming me here today. I'm delighted to speak virtually to the Royal Met Soc. I'm going to talk about, as you've said already, the future changes in the frequency of extreme weather across Europe, and it's not just my own work. There's a lot of work that's been done by various collaborators that you can see on that slide there. Majorly Lizzie Kendon, who I've been working with for over a decade now down at the UK Met Office, a lot of my postdocs and PhD students and some academic colleagues as well, many from Newcastle, but many from all over the world as well. So thanks to all of those people first before I start. So I wanted to start by talking about the summer of 2021, because I think that really it was the summer of 2021 that made us all change a little bit the way we think about extreme weather, actually, and particularly the government in this country. And it was the German floods in particular that made us change the way we think about extreme weather. And I'm sure that all of you will remember the devastating images on television from the German floods, huge amounts of precipitation occurring in just 48 hours from a cut-off low event, caused obviously a blocking high for the Eastern Europe. Cut-off low that firstly caused extreme rainfall over the UK, the Netherlands, and then barreled into Germany and stuck by the Alps, stayed there for a very long time. I was involved in a rapid attribution study after the event, and we found that global warming had made this heavy summer rainfall between 3 and 19% more intense, and around up to 9 times more likely. Of course, that wasn't the only weather or climate disaster that happened that year. And what we seem to have seen in the summer since is a sequence of these very extreme weather events around the world, many of which I believe at least are connected by teleconnections, both at global, regional and local scales as well, and these systems approach. So one of the things the UK government did after this German floods event is to ring round lots of people actually and say, could this happen here? And after that, they commissioned a report by the Joint Committee on National Security Strategy, which looked at basically whether our national infrastructure was ready for these types of storms. And I think it's really important that we think about these types of things. Of course, what they found was that they weren't. So Dame Margaret Beckett led this important inquiry by the National Security Strategy Council, and it was very strong wording actually, so it called for the government to get a grip on climate change impacts. It said there's an overwhelming evidence that climate change is already having an impact on UK infrastructure, and this government must finally recognise that prevention is better than cure and move on from their dangerously reactive approach to risk management. Now, I don't think they've done that still 2 years later. I've also been doing quite a bit of work with Network Rail since the tragedy in Scotland in 2020, really looking at how they need to put weather and climate information into their risk management and operational management within Network Rail as well. There's lots of infrastructure operators still not thinking about these types of things. So I come from an engineering background. I also work strongly on climate change impacts, all the way through from climate modelling, as you'll see in this presentation, all the way through to the sort of downstream impacts and providing information for users to adapt to climate change. So there's a number of key infrastructure vulnerabilities, and I mean, this will come up towards the end of the talk as well, really, when we start to think about how we can apply some of the learning and understanding about changes to extreme events to actually think about infrastructure systems, and in particular I'm thinking about electricity infrastructure systems at the end of the talk. So I'm going to start with some basics. So many of you will know this already. You're meteorologists, many of you, I'm sure, and we know that extreme precipitation intensity increases with temperature at approximately the Clausius-Clapeyron rate. So that's about 6.5 degrees for every 1 degree rise in temperature. And fundamentally, a warmer atmosphere holds more moisture. And this was something that was talked about in a landmark paper by Kevin Trenberth in 2003. And you can see that on the your left there, the figure that shows the relationship between the amount of water in the air and the temperature for different levels of relative humidity. So basically, this relationship holds true as long as relative humidity is kept approximately constant. The other thing that we need to understand, though, is that because the total precipitation actually increases at a slower rate, because the increase in evaporation from the land surface actually only increases at a rate of about 2 or 3% per degree of warming, that actually these intensity increases in the most intense events must be offset by changes in the duration and frequency of rainfall when it occurs. And so the irony of climate change, I suppose, is that actually we'll see more heavy rainstorms and flooding because of this intensification at the high end of rainfall. But then because of these changes in duration and frequency, we're also going to see more droughts and longer prolonged periods between rainfall as well as this heating, of course, that causes more heat waves. And you can see there the type of rainfall that I'll be talking about in much of the talk, which is a very big convective storm, which has occurred over Canada. And you can get these kind of images frequently now from places like Twitter, or X as it's called now. And you can see that this person is standing in the sun watching their neighbour get absolutely drenched by a deluge downpour. It's almost like buckets of water being thrown out of the atmosphere. Of course, that causes flooding. Of course, we see droughts as well. And at the moment, we're only living in about a 1.2 degree warmer world. So we've got a lot of extreme weather to come, as I'll show you now. One thing I have been working on with Lizzie Kendon down at the Met Office for the last, gosh, I don't know, probably 15 years now, actually, since we started this, was the development of convection-permitting climate models. And so many years ago now, and we published the first, I suppose, paper on this in 2014, where we ran a convection permitting climate model. So this is basically a weather forecast model that's able to simulate deep convection. And we ran this weather forecast model and forced it with greenhouse gases and looked at basically what it projected in terms of rainfall changes. And this was really because we knew that the current at the time generation of regional climate models, which were run at about a 12-kilometre resolution, couldn't simulate, or didn't appear to simulate, changes in extreme rainfall in the warm season. in the UK, but also in other parts of Europe as well. And you can see there the difference between the future changes projected by a 12-kilometre model and the future changes projected by our new weather forecast convection-permitting climate model. And what we really found here was when we actually could simulate convection within these climate models, we were actually able to show that the future summer did still become drier on average, but actually it was punctuated by these much more frequent, short duration and very intense rainfall events. And so the intensity increases were around 30 to 70% for short duration events, and this actually tallies with what we'd expect from Clausius-Clapeyron. And we found a 5-fold increase in hourly events over 30 millimeters. So this has really revolutionized climate modeling, and these sort of models are now used all over the world by many different groups in Europe, and they've allowed us to identify aspects of projections using coarse resolution models, climate models that are more robust, and those where we actually need this higher resolution. I suppose alongside this, we've also seen a bit of a revolution led by my group at Newcastle in the last probably 10 years now, actually, in terms of some observational work, where we've managed to collect a new global data set of sub-daily rainfall observations, which has been QC'd. This particular version was QC'd by Liz Lewis and David Pritchard. And this data set has about 25,000 different gauges across the world. You can see the different lengths of the data in the diagram here. And this is really, really good data now. It's been quality controlled, and we can start to then bring our observational data sets and our model data sets together to actually explore processes and to try and understand what's happening with climate change to some of these extreme rainfall characteristics. So what have we found? And so I'm going to start off in the talk by talking about some general findings, and then I'm going to move on and talk a bit about summer storms to start with, and then about winter storms. So in firstly, there'll be seasonality changes to extreme precipitation across Europe, and this is some work that was done by Stephen Chan. And you can see there in the current climate, the season of maximum 1-hour rainfall extremes across much of Europe is summer. But in the future, it moves much more to autumn, even in the UK. The second thing is that, and this is work by Conrad Wasco and Ashish Sharma that's been published in Nature Geoscience. There's a more recent paper as well looking at this from satellite data as well. This was using gauge observations, but they found the same sort of result actually using satellite observations recently as well. So they've looked at the storm profile. So this is the temporal profile of the storm. You can see they've divided each storm up into 5 segments, and they've looked at basically with temperature how these segments change. And actually they find that the most intense part of the storm gets more intense with warmer temperatures. So the storm gets more intense at its peak. We found this in climate models as well. And the other thing is that there's been quite a bit of work looking at changes to storm size as well as intensity. And this really differs on whether you use observations and whether you look at, I suppose, dry or arid climates or quite moist, humid climates. And actually, when they looked at Australian data in a quite arid context, Conrad Wasco and colleagues found using observations that basically, and you can see this here on the left for Australia, that in warmer temperatures, the storm becomes more peaked in the centre, but it also reduces in size. And you can see that in the red line there compared to the blue line for the colder temperatures. So Kai Lockbeiler and Gert Lenderink looked at this for the Netherlands as well, using radar observations in this case. They actually reversed the colours on the lines very usefully. So they used red for the cold storms and blue for the warm storms. But what you can see there is actually the storms intensify and become larger with warmer temperatures in the Netherlands in a humid climate. And Andy Prine did some work on this using a convection-permitting model projection for the USA on the far right there. And you can see that the climate model projection for the USA showed that the storms in the model become both more intense in the peak and they become bigger as well. So the jury's out a little bit on what's going to happen to storm size with global warming, but there seems to be some evidence that in more humid locations where there's not a lack of moisture availability, these storms may well become bigger as well as more intense, whereas in more arid regions, and it makes physical sense, they may become more intense but smaller in size. So there's those limits on the moisture availability for convergence into the storm. So I'm going to move on to talk specifically about summer storms and some of the work we've done on that over the last few years. So going back to the German floods, we just published a paper in 2021 when the German floods hit. And our paper was really relevant actually to the floods that hit Germany in 2021. And what we'd found in this paper, tracking storms across Europe and looking at the changes to the storm characteristics for the warm season storms, so the summer season storms in Europe, for the current climate and the future, is that slow moving storms could become 14 times more common over land by the end of the century. And this is exactly the type of storm that hit Germany in 2021. So obviously very much picked up by the media. The problem with a slow moving storm, of course, is that actually the slower it moves, the more ability it has to dump rain over the same area and the greater risk of serious flooding. So this was work led by one of my postdocs, Abdullah Karaman, who's based out at the UK Met Office. And he found that as well as a massive intensification of storms, and you can see there, particularly in the Mediterranean, we found that there was a massive intensification of particularly 1 hour peak precipitation in these mesoscale convective systems in the future climate, particularly in the autumn. But you also found that in other months further north. There was also this big increase in the slow moving storms. And this we related back to a weakening in the jet stream, which we have seen in observations as well. This causes the storms to move more slowly in the future. And I think one of the important implications from this as well is that you need to look at total event rainfall. We often, when we're thinking about flood risk, we actually just look at things like peak intensity to understand flood risk over a certain duration. Whereas we actually need to be thinking, if storms are going to change in size, we need to be also thinking about total event rainfall over the whole catchment. So that includes duration and spatial extent as well as changes to intensity. So I said in my abstract that I was going to talk a little bit about dynamics as well, which I will do now. So this is some work done by Stephen Chan, who's now at the National Oceanography Centre in Southampton, but was at the time working with myself. So he used this storm tracking information and looked at the changes in precipitation volume in the warm season from mesoscale convective systems. What we did was we compared two different convection permitting models, and one was from the UK Met Office, and that one was actually driven by a global climate model that included changes to the large scale dynamics within it. And the other one was what's called a pseudo global warming approach, which was run by ETH Zurich. And that actually really just looks at the thermodynamic or the warming changes at the boundaries of the model. So we ran European scale models and we tracked the storms and we looked at the changes to precipitation volume. And what we found in the top figure there, you can see, it's quite hard to tell, but I will basically summarize. So basically the mean precipitation or the volume of storms, volume of precipitation per storm in general goes down in both models in the future. So that's what we'd found with previous studies. But what we also found is that the volume of rainfall coming from convection, from these mesoscale convective systems, went up substantially in both models. One of the surprising results, however, was that we found that the number of mesocell convective systems only went up in the model that was driven by these changes in large-scale dynamics. And when we only included the thermodynamic signal, the warming signal, but not the changes in large-scale dynamics, we didn't see this change in the frequency of the mesoscale convective systems. And so this was an interesting result, and it really suggests that actually the dynamical changes are really important for some of the characteristics of changes to future storms. And so, you know, consistency in both the top 10% of mesoscale convective systems account for about 80% of the total precipitation across Europe in the summer in both models in our future runs. So we're talking about huge amounts of precipitation here. And the mesoscale, the precipitation from convective systems increases, it triples over the British Isles in summer. And you can see here, these show the numbers. So it's basically going up to nearly 50% of all rainfall will come from these convective storms. This is by the 2080s under an 8.5 scenario for the British Isles. So quite dramatic changes potentially, and the potential for lots more flash floods in the future. But large-scale dynamics are important here. And so we return to the summer of 2021, and this is a slide put together by Paul Davies, who's the chief meteorologist at the UK Met Office, who I've been working with quite a bit recently, really thinking about how these teleconnections can be used to better forecast weather extremes and to predict, in particular, very short duration extreme rainfall. Often these very persistent weather extremes are caused by this blocking pattern, this wave pattern across the whole globe, actually, and you can see these waves and nodes in the atmosphere here, the blocking across the Northern Hemisphere. And this blocked pattern in the summer of 2021 caused a number of persistent weather extremes across the globe, and that goes all the way from the US Canadian heat dome, the New York floods, the floods in Germany, there were massive floods in China as well, and Siberian wildfires as well. And all of these systems are connected and sequential, and we're working on this type of thing in terms of improving forecasts at the moment. And you can see this shows this summer now. So this was July, the second half of July this year, and you can see the same blocked pattern emerging. And of course, we've seen these persistent weather extremes now for at least the last 3 years across the globe, every summer in the Northern Hemisphere, and actually every summer now in the Southern Hemisphere as well. We're starting to see these same blocked patterns and very persistent, both floods and droughts, or heat waves rather, and wildfires, connected systems which cause weather extremes. In summer 2022, we saw the same blocked conditions led to a heat dome over Europe. We saw 40 degrees in the UK. We saw records broken in many locations. We've seen the same types of events again in 2023. They didn't get quite as far north as the UK this time, but they certainly broke records again in parts of Europe. We've seen massive storms as well, which I'll talk about a little bit later, in Europe as well this year. So this is a paper by Russi et al., basically published in Nature Comms, where they looked at heatwave trends over the mid-latitudes in Europe. And they found there have been increasing heatwave trends over the mid-latitudes, and particularly Europe. And you can see the places there, and there's particular locations where there do appear to be really big trends in heat waves, and particularly massive increases in intensity as well over parts of Europe. And you can see that blocking there. And often the blocking is set just to the east of Europe as well, actually. And that quite often causes very extreme rainfall over parts of Europe, like the UK, when we get the blocks in this place, because of this double jet that then forms. So we're seeing increasing heatwave trends, and this has knock-on effects for other weather as well, I'll argue in this presentation. In particular, one of my students who's just graduated from Strathclyde University looked at the links between heat waves and extreme rainfall. And he firstly defined a heat wave, and you can see here, so he's defined a heat wave as if the daily maximum temperature lies above the 95th percentile for at least 3 consecutive days, and the daily minimum temperature lies above the yearly 95th percentile for at least the second and third day. And then he's basically said when they drop below that, basically it ends. And you can see here, this was actually for Australia, this particular diagram, and you can see the number of heat waves there that happen in their warm season from November to March. And what he'd done then is looked at how the heat wave is then connected to the occurrence of extreme daily or hourly rainfall amounts. And the heat wave ends at that 0 point on the x-axis there. And this is an example of a heat wave followed by an extreme hourly rainfall from a station in Germany. And you can see on the plot there, the temperature plotted, the Tmax and Tmin as the red and orange lines. And you can see the rainfall plotted in the blue line. And this shows that there was indeed an extreme rainfall event following the heat wave in Germany for this case. The rainfall was defined as extreme if it exceeds the 95th percentile for the hourly wet amounts. And we used the quality controlled rainfall observations from the global subdaily rainfall data set, which basically I described earlier. And all of this work is published now. He's got a series of 3 papers that have come out on this, actually one of them talking about the mechanisms as well. So what he and we found was that basically there was quite substantial evidence, and this is using observations. We're not now talking about future projections. We're talking about observed relationships in data between heat waves and extreme rainfall events following heat waves. And you can see that when we looked at this global data set and we looked at different climate regions there on the bottom plot, basically that these compound heat wave followed by extreme rainfall events are much more likely in temperate or colder climates, provided there's no dry season. And basically in some parts of the mid-latitudes, and particularly in Central Europe, actually, in the UK, more than 40% of heat waves are followed by these very extreme hourly rainfall intensities. And just to say that, to put this into context, gauge data is really sparse. I would like to repeat this analysis with radar data because actually gauge data only captures about 15% of hourly extreme rainfall because of its sparsity. So I think that we're probably underestimating here the amount of heat waves followed by hourly extreme rainfall in this case. So there's this compounding effect that matters. And so basically this is a picture of some of these large scale dynamics, and you can see this is the omega block that we saw earlier in the year associated with that Storm Daniel over Greece. And Storm Daniel dropped 3 years worth of rainfall in 2 days, which is quite staggering, quite honestly. And you see a similar cutoff low occurring over Spain there. We also had huge hail occurring over the Balkans and extreme hourly rainfalls as well. And all of this stuff is, I suppose, what I'm trying to convince you of in this presentation is that all of this stuff is connected in one system, and all really important actually for predicting and estimating changes to extreme weather. That Storm Daniel over Greece then turned into a tropical cyclone, a medicane, as it's called in the Mediterranean, hit Libya and caused that devastating flooding, dropping 400 millimeters of rainfall in just 6 hours. And those dams failed and all those people died. These are really, really big and important events, and they are on the increase, but they are all connected. So it's really important that we try and study the types of weather and the types of synoptic variability that are actually causing these types of events. And again, this is some work that was done by Stephen Chan just before he left my group. And we looked at the types of European weather regimes that actually cause these extreme short duration rainfall events in the UK. And what I'm showing here is the future changes in weather types from the climate models in UKCP 18. And you can see that for different time periods from 2010, which is the sort of current climate, all the way up to 2070. And you can see on the left, the actual weather regimes themselves, the mean sea level pressure for those regimes. So I'm highlighting a few there in terms of their changes in frequency on the right, and in particular, number 1, number 5 and 6, and are ones that cause very extreme rainfall, and number 11 as well is the same. They cause these very extreme hourly rainfalls across the UK. And you can see on the left that actually those are the events that are increasing in the, those are the weather types that are increasing in frequency in the future, but also the ones that cause these very extreme hourly rainfall events as well. So they're important. I would say that climate models are not simulating the type of dynamical changes that we're seeing in reality at the moment. They're very much underestimating these changes in the waviness of the jet, the slowdown of the jet in the summer, but yet they're still producing increases in these types of weather patterns. But I imagine they're probably underestimating the potential for these changes. And when we looked at, this is now looking at a polar view onto Europe. This was some work done by my PhD student, Anna Whitford. When we looked at this in terms of the weather pattern 5-6, and those events that had produced 40 millimeters of rainfall in three hours, or over 40 millimeters of rainfall in 3 hours, and those that hadn't produced any rainfall, when you look at the difference between these types of events in terms of the mean 500 hectopascal composite anomaly, you actually see this wave pattern emerging. So that's the difference at the bottom there. And you can see that actually it's this strong wave pattern, this blocking pattern around the globe that seems to cause these events as well. Now, these teleconnections do exist and they do matter, and they are really important for forecasting as well. And I think we really don't know enough about them at the moment, but you know, we're starting to get some inklings that actually all of these things at global to local scales matter for these changes to extreme events. So I'm going to move on very briefly and talk about lightning changes. This is some work that was done by Abdullah Karaman and published in 2022. So we found that lightning in our convection permitting model. I mean, this is the nice thing about convection permitting models. Actually, you're not just able to resolve convection, you can also produce projections of changes in things like lightning and hail and other types of extremes that we're not able to simulate in these coarser resolution global climate models and regional climate models as well, actually. So important takeaway points here are that these types of convective storms massively increase in the Mediterranean region and over the Alps in the autumn and summer months, and in the summer over the UK as well. And actually, the dynamical changes are really important for changes to lightning as well, in the sense, and particularly this northward shift in the jet stream in the summer that's projected by many climate models seems to be really important. That produces more lightning in summer over the UK. And the weakening of the jet as well, the weakening of the jet as well is important in this sense because of that slowdown of storms, as I've said before. There's also, in general, because of the melting level height becoming higher, we get less hail. But actually, there seems to be the potential, and I've not shown any slides here because we're trying to get this work published at the moment, but there seems to be the potential for very large hail in the future climate as well. So moving on quickly to talk about winter storms. This is some work that's really been done by Colin Manning, together with Lizzie Kendon and others at the Met Office. One nice thing about convection permitting climate models and their very high resolution is we're able to resolve features like sting jets. And many of you might have heard of a sting jet, particularly because there was one associated with Storm Eunice just last year. And we wrote a piece in the conversation about it that there's a link for there if you're interested. But a sting jet is something that wasn't really discovered actually until about a decade ago. They think there was one as part of the Great Storm in 1987. And there's something that basically is very, very fast airflow that descends from the mid-troposphere, basically within a Shapiro-Kaiser cyclone, and comes down between the warm and the cold conveyor belt. And it doesn't always hit the ground, but if it does hit the ground, it basically produces these very, very narrow but very intense wind gusts that tend to cause quite devastating impacts. So what we did was we actually looked at windstorms from our convection permitting model. And in this case, we're just looking at the UK, and we looked at the changes to windstorm severity. And you can see on the left there that basically the future windstorms are projected to be much more severe by about 20 to 30% than we see in the current climate. So a 10-year event, for example, is projected to occur about every 5 years in the future climate. But what was interesting was that much of this change comes from the contribution of sting jets. And actually, we see many more storms in the future that are both these Shapiro-Kaiser warm core storms, and they also have sting jets as well. And you can see that on the left there. Right, rather. Sorry, I can't do left and right. Right there. So we basically took footprints of all of these different storms, and what we're interested in is whether the joint extremes from wind and rain actually change substantially within these extratropical cyclones. And so we took a rainfall footprint and a wind footprint that obviously moves in time from these extratropical cyclones. And we looked at the changes for different return periods and the overlaps for the control. For the future, we looked at the contribution from temperature only, and then for the future, looking at both the dynamical and the thermodynamical temperature changes. And we found that there was an increase in the land area experiencing combined wind and rain extremes in the future, and it's not explained by just Clausius-Clapeyron. So basically, there must be some contributions from dynamical changes in that future change. So we then started to look at the drivers of these combined windy and wet extremes. And you can see there, looking at the cyclone composites on the left, that we should know this already, really, for extratropical cyclones, the wind extremes happen in a different part of the cyclone to the rainfall extremes. So you can see there, the wind extremes are happening in that southern part of the cyclone. The rainfall extremes happen in the northeastern sector. And when you combine them, you get the extremes occur within this region of the warm conveyor belt between the warm and cold fronts. And you can see that in the green there. And then we looked at cyclone track densities and how those were changing in the future as well. And so, you know, the actual cyclones transiting the Atlantic, how will they influence the footprints? And so what you can see here, and again, I'm going through this quite quickly, so you're very welcome to have my slides afterwards, and we're trying to get this published at the moment. But what we found is we looked at all cyclones for the control and future, and then the changes, and then we looked at changes in wind, changes in the rain, and changes in the ones that had compound extremes. And what we found was quite significant about the extratropical cyclones that were producing these wet and windy extremes in the future was that they're very much a more southerly direction. So they come in further south, so they're warmer, they're able to pick up more moisture, but then they have a much sharper deflection when they hit land as well. And so this contributes to a change in the dominant wind direction to a more southerly direction as well in the future. And you'll see in a second, this is quite important for consequence forecasting. So just to finish off, I wanted to tell you a little bit about what we've been doing, and this is work led by my husband, actually, Sean Wilkinson. So he's been doing some work for quite a few years now on consequence forecasting, and this is basically trying to establish a system for forecasting the consequences of extreme weather, rather than just forecasting the extreme weather themselves. What we've done here is we've taken an example working with the electricity companies of looking at wind-driven electricity faults. And you can see Colin Manning's put together a number of contributing factors in this diagram here. So, for example, wet soils, So you might get more trees falling over onto lines because the tree roots are less anchored in the soil. Strong winds give you an increased probability of trees falling over and branches breaking, and wind from a non-prevailing direction might give you trees that are more vulnerable to falling over. For example, what happened in the northeast when we got Storm Arwen, and huge devastation when we got our wind coming from the northeast in very strong winds in Storm Arwen. And so we looked at what effect some of these things had on electricity faults in windstorms. And you can see there on the left, the number of faults in the windstorm compared to the maximum wind gust. Also for preconditioned rain over the 80th percentile or below the 80th percentile. And there on the right, you can see the number of faults occurring from these storms in both dry and wet soils. And what's really obvious from that diagram is that actually you get much higher faults for windstorms occurring in wetter conditions. And this is quite relevant to the future. We've just shown you that actually there's going to be many more of these wet and windy storms in the future, and particularly wetter storms. So that's really relevant for impacts. The other thing is the influence of wind direction itself. Basically, we found that fault numbers tend to be higher in windstorms with winds from the south than winds from the west or southwest. And actually, this is relevant as well, because we're expecting that many more of those storms are going to be coming from a southerly direction in the future from what we show with our climate models. So actually, the potential is for not just the changes in the wind to matter for these impacts, but also the changes in the preconditioning of the rainfall and the wind direction as well. So all of these things matter. And I think it's a really nice way of both looking at the potential for climate change impacts, but also looking at consequence forecasting in terms of forecasting the potential impacts of oncoming storms as well. So finally, some future directions and thoughts, and I've got just a few slides now. And these are quite potentially profound, but maybe not. So I really work very closely with lots of different areas. So I work on observations. My group works on climate models with Lizzie Kendon down at the Met Office. I also work quite a lot on weather forecasting with Paul Davies. And I think that really key to understanding the future and future changes is actually better connecting all of these fields and really thinking about the causal pathways and the processes that actually cause these extremes, whether that's of rainfall, whether that's of hail, whether that's storms, and how they're interconnected in time and space. Because unfortunately, climate models are just models and weather forecast models are just models, and they all have biases. Some systematic and some just, we're not going to actually fix potentially. And we need to know with much greater certainty for climate adaptation and building resilience in infrastructure networks, what is going to happen in the future. And I really do think that this works by Ted Shepherd down at Reading University. I really do think he's right that actually these causal networks can provide a framework within which we can extract relevant climate information. We can bring lots of different parts of information from different pathways together from both observations, weather forecasting and climate model to actually describe scenarios of what might happen in the future. And part of the way that Ted has suggested that we do this, and I was part of this publication in Climatic Change in 2018 as well, is that we actually use this process understanding and expert judgment to produce storylines of plausible extreme events, and these can then be used for risk assessment. And I think that this is something now that's being tested out and used in lots of different places, and that we can therefore produce these storylines of plausible extremes, which perhaps climate models can't produce because they're unable to produce some of the dynamical situations that we see in the real world. And this allows us then to actually test out some of the strategies that we might need for resilience planning or for operational planning during emergencies. So one of the projects that I've had, Stormy Weather, was really doing all of that work on extratropical cyclones over the UK and trying to understand the projected changes. And so what we try to do in this slide, and this is just a demonstration of how this might work, and it's not finished at all, but really it's trying to bring different parts of the puzzle together from different, from observations, from climate models at different resolutions, so from convection permitting and from global climate models and from weather forecasts as well, to really give us a better understanding of what might happen to these extratropical cyclones and these storms over the UK with about a 4-degree warming. Now, that might be higher than we think is going to happen. At the moment, we're looking at about a 3-degree warming by the end of the century with the current pledges. But you can see that we've split this out to look at so more intense storms. We're looking at about a 30% increase in the intensity of windstorms, increased contribution from sting jets, larger wind footprints, so bigger storms basically, increased convection. And then we get these big increases in hourly rainfall intensity as well as the rainfall footprint. So the footprint volume increases by about 70%, so that's massive. And then we get an increased frequency of these storms as well because of this warmer jet and the more southerly location of the jet. We get many more cyclones with extreme wind and rainfall footprints, which we don't really get at the moment, actually. And so these are much more likely. So this is, it's not painting a pretty picture of what's going to happen in the future, but it allows us to start to bring together some of these results from different studies to actually build these storylines and causal pathways. So to finish, there's strong evidence that rainfall extremes increase with regional global temperature. You can see a diagram here trying to show some of the process pathways to this, which was published in Nature Reviews in 2021. I think that bringing results together from observations and new very high resolution convection permitting models has provided a much greater understanding of the thermodynamic drivers. We're now trying to move towards understanding the dynamic drivers as well. There's certainly a need to update flood risk estimation methods and climate allowances for extreme rainfall changes. I think final thoughts are that I actually think that these compound extremes and these the sequencing of extremes and the combination of different types of extreme weather in sequence are really important for impacts. And they actually may change much more than individual extremes with warming. And they're often connected by physical processes in kind of almost known sequences that might be important for impacts. I think I've shown that dynamical changes to the atmosphere are really important for changing characteristics of extreme weather. My worry is that global climate models are underestimating these changes that we're seeing in the real world, and they're really underestimating the persistence of block conditions, which are important for heat waves and extreme rainfall and these persistent and large flooding events that we're seeing around the world. And these seem to be increasing every year. So my thought is that we need to take a new approach, actually. We can't just rely on climate models to tell us about the future. Maybe we shouldn't ever have done this, but we need to combine information from regional and global climate models with observations, with weather forecasts, and think about biases and within these models and systems as well. And finally, I think that the transitions between weather pattern sequences are crucially important in producing these extremes, particularly compound extremes. And I think this merits further investigation, both for the future projections, but also for weather forecasting itself as well. So I'm going to finish there. Thank you very much for listening.
Thank you very much, Professor Fowler. Unfortunately, with online meetings, you always get this slightly underwhelming close to the talk, but I can assure you in person you'll be getting a very warm reception. So many thanks indeed for.
Should I stop sharing or not?
Possibly not, because it may be that some of the questions refer to some of the slides, perhaps. They often do, but we can run with that for just now. So we'll move on to a Q&A. Once again, thank you very much for that. I've got a few questions myself. As I say, previously, we've kind of written questions in the chat and I've read them out and kind of interacted that way. If people wish to do that, then please do, and I can do that. But otherwise, we'll try a sort of, if anyone wishes to ask a direct question, then we'll try with that one first. I know we've got a few climate experts in the audience as well, so hopefully for some good questioning. I'll be slightly selfish and take the first question, if that's okay.
Yeah.
take my opportunity, and also slightly selfishly link it to my own kind of line of work. I'm fascinated with what you've outlined there and your studies and various connections of how do you think we can improve how we warn for and communicate, particularly sort of extreme intense precipitation, and in particular sort of short lead-in time events, a bit like the tragedy we had in Stonehaven a couple of years ago, that type of event. How do you think we can improve how we warn for and communicate that both with the public and with industry?
I mean, so I think firstly we can try and improve the actual forecasts themselves. Our current weather forecast models are not very good at actually simulating these types of events. So although they're the same models used for our climate projections, they're still not great actually at simulating these type of events. I'm working on some new methods, I suppose, for trying to predict or provide better predictions for these very short duration downpours with Paul Davies. So we're kind of working on a series of papers which look at these processes in different parts of the world, but it seems like there's quite consistent processes and ingredients that you need to include in the weather forecasts to produce better forecasts. And that's one of the things we're hoping to test next summer, actually, in a sort of sandpit trial. I think it's not just about that, though. So it's not just about actually producing better forecasts, if you like. It's about the transmission of those forecasts through in the right way to the public as well. And I know that the event was different, but the flooding event in Germany in 2021 really showed the failure of that by the German authorities. 200 people died in that event, and really no one needed to die in that particular instance because that flood was forecast well in advance. Because it was a cut-off low, it was relatively easy to forecast, and the amount of rainfall and even the floods it produced and the levels of water were forecast. But they didn't have a good enough system of getting that information out there to people, and it happened at night. So all of those flood banks, failed during the middle of the night as well, which is never a good time for people to escape. So I think there's a lot that needs to be done in terms of communication as well. And it's not just about sort of giving people information saying, right, there's going to be an extreme rainfall event, but it's giving people information on how they should behave as well. So Paul Davies always says to me, if we'd had a better forecast of the Boscastle flood, people would have died. And actually no one died in that event. But because the event wasn't well forecast, people didn't go outside and get into their cars and try and drive away from the flood, and they weren't swept down the river. So, there's important information to be understood by the public as well about how to use the information from forecasts, and how to behave when you receive one of these forecasts. So it's about education as well. And I honestly don't know exactly, but there's got to be lots of different stages to this. Improved forecast, but also improved information to the public and particularly information on behaviour.
Thank you. That's fascinating. I could go on, but that's fantastic for now. I see David Stevens has got his hand up, and there's a question in the chat. So I'll go to David first, please.
Yes. Hello. Can you hear me?
Yeah.
Yeah. Okay. And I've turned my camera on. I can't tell if you can see me or not. Anyway, thanks very much for a fantastic talk. That was brilliant stuff, Hayley, and very scary. I had a quick question about wondering why the climate models don't really produce the right trends. And I'm always interested that when I teach stuff about cloud physics and so on, we always say a lot about CCNs and aerosols being important. And I know climate models are a bit rubbish at representing aerosols and their impacts. And I just wondered if some of the underestimation or some of the lack of skill in climate models is perhaps to do with the aerosols. And I just wondered if you could comment on that, and whether that's just a complete non-starter or whether that might be the case.
Yeah, I mean, so it's a good good point. I think, I mean, a lot of climate models now do include aerosols and even dynamic aerosols within their simulations. I suppose the honest answer is I don't know how much it matters, and I don't know that anybody does. I think there's quite a lot of thought being given to why extreme weather seems to have shifted dramatically in the last 3 years. And one of the explanations I've seen from, the real world, as it were, not the model world, is that they banned the emission of sulfate aerosols by ships in 2020, and actually that the reduction of the amount of sulfate aerosols over the oceans, particularly in the northern hemisphere, may have actually caused this sudden shift to a much warmer climate, which you can see in the observations, particularly this year, warmer oceans and more extreme weather. So that's from the real world. I think in the model world, the models don't produce these blocks, or they do produce these anticyclonic blocked conditions, but they don't persist for long enough. And that could be to do with aerosols, but I think it's probably more likely to do with a deficiency in land surface schemes, for one. So I think they don't last for long enough because they lack that feedback with the land surface. The other thing is there's definitely deficiencies in Arctic processes. And so you don't get that same sort of temperature gradient that you're seeing in the real world, I think, between the equator and the poles. And I suppose the other thing is that you don't get that. So the transfer of the heat that you see in the real world and that moisture from the tropics, because those eddies can't happen on the sort of coarse resolutions that global climate models run on. So no one knows, right? But I think it's almost certainly a combination of different things. Some people think that if you manage to move to kilometre scale, global climate models, you'll solve all of these issues. I suspect you won't. But for whatever reason, they don't produce the sort of persistence in the blocks that we see in the real world. But I will say that the weather forecast models don't really do that either. So there's something wrong in both the weather forecast models and the climate models, which means that we're not capturing this really crucial change in dynamics that we seem to be seeing.
Thanks.
Thanks both. So we've got a couple of questions in the chat function. They're actually sort of linked, so I'll sort of link them as one and see how that goes. And if the question askers wish to come in, then please do. And both questions, you may have to see them yourself actually, Hayley, but they're regarding scenarios. And the first question is, how do the results compare with the RCP 4.5 or the SSP2 4.5 scenarios? And the second question is, what happens to the storm dynamics if global warming, as some have just suggested, is significantly greater than the IPCC's mid-range outlook? Do storm impacts merely double? So it's kind of two questions there, sort of linked to how do the results and your findings link to varying scenarios?
Yes, they're sort of two sides of the same coin, aren't they? So, I mean, we have not run our convection permitting models for the 4.5, RCP 4.5. But I mean, if you believe in sort of the temperature scaling approach, then you would expect that obviously that the effects won't be as big for 4.5. But I mean, we basically ran the RCP 8.5 because most of the global climate models in CMIP 6 and CMIP 5 have been run for that particular scenario. I mean, basically, whatever we can do to reduce greenhouse gas emissions and reduce the change in temperature is good, because we absolutely know that the thermodynamic signal, that increase in temperature, is increasing, for example, the intensity of rainfall extremes and other types of extreme events. So anything we can do to reduce that is good. I suppose the opposite is true as well. If we see even bigger warming, then we can expect all of these types of things I've been talking about to become even more extreme. Yeah.
Thank you. Hopefully answers the questions, but it was nice and clear. We've got another hand up. Jeff, want to ask your question, please?
Yeah, hi. I was interested in what you were saying about winter storms broadly in the southwest approaches and Brittany, and that they would be increasing. I did a bit of work when I was with the Met Office in the late 1980s, and I was looking at some storms, starting with the Fastnet storm in around 1979, and it was really focused around the 1987 storm. But when we looked at it, there were quite a few really intense lows that took a much more southern track, if you like, than the climatological mean, somewhere between Scotland and Iceland. So they've always existed. Perhaps you're not saying that they've always existed, but there's been quite a few, and for a couple that went into Brittany around, I can't remember, it was 1999, 2000. Yeah, there was another one last week. But yeah, I don't know what you think about that.
Yeah, no, absolutely. I guess what I'm not saying that they haven't happened in the past. Absolutely not. But what I am saying is we expect those more southerly storms to be more frequent in the future. And I think there's a particularly interesting point, and I'm involved in a project called Hurricane, which is led by Reading University. And they're actually looking, or we are actually looking at the likelihood of tropical cyclone to, extratropical cyclone transition. So we're looking at that kind of transition from the tropical cyclone that hits the US, and then all of that energy is transferred into the extratropical systems, which then hit us normally. But at what point there may be much stronger storms that actually hit the UK, and how important is that going to be? So that's quite important as well, because quite often in the autumn, a lot of our extratropical cyclones used to be tropical cyclones, actually. So it's that transition is really important as well. And if that starts to happen in a different part of the Atlantic, that might be really important for storm characteristics in the UK as well.
Yeah, thank you. I mean, the other half of that question, although it's probably not something you've looked at, would be, does that mean that perhaps as a percentage of the total number of storms, there will be more that take a southern track rather than the more traditional tracks? You probably haven't looked at that again, but that would be very interesting to know or have a feel for.
Yeah, I mean, I think since we've basically taken a composite across all the storms. So yeah, I mean, that's what it shows basically, that those southerly storms as a percentage of the total are becoming more a larger percentage. Yeah, absolutely.
Yeah, thank you.
We have another question in the chat, which again might just about link with that previous discussion just there. And again, it's a question about changes in winter storms, referencing the strong convection that we saw near the cold front of Storm Ciarán, with large hail and strong tornadoes in the Channel Islands. So the question is, what are your thoughts on potential compound extreme events as far as severe convection in warmer and wetter cyclones is concerned? So I guess changing climate, but in the winter. Are the signals for this in your simulations is the question.
Yeah, you're right. Actually, I should have included this as well. That's quite interesting. I'll have to include a slide next time I give this talk. But yeah, so Lizzie Kendon has done quite a bit of work on this, and I haven't been involved in that work as an author. But she's looked at how much convection within, I suppose, how much rainfall comes from convection rather than sort of, I suppose, frontal processes in the winter in the future climate compared to now. And she found that basically a lot of these systems, these extratropical cyclones, have a larger proportion of embedded convection within them in the future climate. And I think particularly that's particularly important for also producing some of these extremes like we saw in Jersey, and the tornado and the giant hail and all of these kind of things. And obviously it's important in summer storms as well. And we've seen giant record-breaking hail in parts of Europe this year, for example, a couple of times. We've seen tornadoes in Switzerland. we've seen massive lightning storms and flash floods as well. So it's important in the warm season, but it also seems to be becoming more important in the cold season as well. And obviously, that's really important. Yeah, I mean, I will say we haven't looked yet at compound extremes from the sense of convective storms. We've tried to get funding to look at this, but we haven't been successful so far. But I'm hoping, we actually had a reviewer say this about 6 months ago, actually, with our latest try, tornadoes aren't important and won't be important, in a future climate. I don't know why you're interested in them, pretty much. I'm paraphrasing. And then of course a tornado happens in Jersey. So I'd like to think we've been vindicated at least, but it's obviously something that's going to potentially increase in the future as you get more convective storms and mesoscale convective systems in particular. The honest answer is I don't know. We know there's more convection. We don't know anything really so far about these linked processes, but it's something we're really interested in looking at further.
Great, thank you. And thanks from Lars, who asked the question. We have one more question from David. We'll call this the last one in the interest of time, but some great questions and answering. Thank you very much, everyone. David, do you want to ask the question again yourself, or do you want me to?
Yeah, sure. No, I can do. It's a rather obscure question, perhaps, but I was wondering about proxy methods that might let you extend records back in time. And I mean, things like tree rings for temperatures and so on. But is there any equivalent for sort of looking at storms or extreme precipitation, or even things like blocking into the past? And I suppose I'm wondering even if you can go as far back to something like, past really hot climates that might be giving you similar dynamics to present day. So I guess I'm asking about paleo kind of modeling and whether that might tell us anything.
I think that because the timing is so important in terms of the sequencing and the interactions, that we'd be very unlikely to get that detailed information from paleoclimate information. Yeah. But I think one thing that is really important and we really need to do, and I was talking to Ed Hawkins about this on Tuesday at a meeting on data rescue. There's huge amounts of data, and it won't be just the UK and the UK Met Office that hold archives and reams and reams and reams of like paper records, right, of rainfall. There's also the same sort of information about flow, which the Environment Agency and other organisations across the UK hold. And all of this stuff needs to be digitised, quite honestly, because it's really important for trying to understand climate variability and our risk, baseline risk. Ed's done some work over the last, well, you may have seen this just as the pandemic started in 2020. He did this weather rescue project, which was on the BBC, and he managed to, because everybody had nothing to do but sit in front of their computers inside, they managed to do 16,000 observations or something, gauges in like 9 days or something ridiculous like that. So they basically finished the entire project. They managed to translate all of the monthly rainfall records back to early in the 19th century for the UK into digital information. And he's recently looked at this information, and this is only the monthly records at the moment. But what it's shown us is there were much bigger drought, dry years of dry sequences of dry years in the 1850s, for example, and wet years as well, early in the record, than there have been in recent years or in the last, say, 100 years or so. So really, it's told us a lot about the interannual and intermonthly variability across the UK. There's also a huge number of daily records that could be digitised, but it's going to take quite a lot of investment by government to actually do this. There's also, really interestingly, there's rainfall data that goes back to the 1930s for hourly records as well. And they also contain information on things like 15-minute intensities, etc. So it's a little gold mine, quite honestly. And I think that relating that to things like weather patterns, because we've got mean sea level pressure records back a long way as well already, that have already been reconstructed. And so that sort of data could really be very, very useful in trying to extend our records. I'm not convinced paleoclimate data would be that useful, but we really should be investing in rescuing this data, particularly because it's gradually deteriorating over time as well. And also the expertise needed to actually, particularly for the flow data, to actually read the flow graphs and things like that. People are retiring and gradually, dying, and we're losing that expertise that we need to actually digitize this data. So really, really exciting, really interesting, and I think could be really important as well, that sort of thing.
Thanks.
Thanks again. So thanks all for, once again, thanks Hayley for a wonderful talk, and thanks everyone for engagement and their questioning. I thought it was a really, really fascinating session. So that leaves us, as I say, many thanks. And our next talk is the 8th of December, Friday the 8th of December. And we've got Dr. Kerry Nicol coming up from the University of Reading, and potentially linked to some of the talk tonight. And this will be looking at the electricity of extensive layer clouds. So it should be quite an interesting talk to attend. And that's going to be in person as well. So we'll be running that one again as a hybrid meeting. So those that wish to and are able to, please join us in the University of Edinburgh. We'll have a nice meeting beforehand and hopefully some mince pies, etc. And otherwise, please join us online for the hybrid section. So thanks again, everyone, and I wish you all a good evening and a nice weekend.